We will now continue with our study of electric fields by looking at electric field produced by extended charged objects. Now, what is the difference between this and what we did in the previous class? In the previous class, we talked about electric field produced by point objects. For example, you have the charged object here, which is a point charge, and we obtain the electric field E at a distance r as kq over r squared. Now, this is the equation for electric field at a point, distance r from a charge q, a point charge q. All right, this time the electric charges are not point charges but distributed over an extended object. Like what I am holding is an extended object. It is not a point charge. All right, we will be considering charges that are carried by extended objects. All right. So far, we discussed electric field due to point charges. Gauss's law will help us study electric fields due to extended charged objects. We will be discussing this Gauss's law later in the lesson or in the second part of this lesson. And then in the next lesson, we will be using Gauss's law to obtain electric field due to extended charged objects. But now we will use the formal calculations to find such fields. In order to study electric field due to extended charged objects, we will define some terms first. All right, what are the terms? First term that we need to understand is what is linear charge density. Suppose I have an object, a long object like this, and this carries an amount of charge Q. What is the linear charge density? In other words, what is the amount of charge per unit length? That is linear charge density. So this is the charge per unit length of a charged object, and it is measured in coulombs per meter. If Q is the total charge that is on an object of length L, then lambda, we will represent linear charge density using the Greek letter lambda. The lambda will be equal to charge per unit length, Q over L. And what will be the unit for measuring charge per unit length? It will be coulombs per meter. The second quantity that we will discuss is charge per unit area, surface charge density. Now, suppose I have an extended charged object like this. Now, this surface carries a charge Q, which has an area A. Then, the amount of charge per unit area is called the surface charge density. So, surface charge density is the charge per unit area, and you measure it in coulombs per meter squared. If Q is the total charge on an area A, then the surface charge density represented by sigma. We will use that very often as we move on. Surface charge density is represented by sigma equal to Q over A. Now tell me, if I have this basketball, I keep this basketball always with me. Now, if there is a total amount of charge Q distributed over this surface, anybody tell me what is the surface area of a sphere? The surface area of a sphere is 4 pi r squared. So, if I know the total charge on this surface, and if you divide that total charge by the surface area, I get the surface charge density sigma. And that is something that we will be using as we move on. And the third quantity we will be using is volume charge density, represented by rho. Well, that is simple now to understand. In other words, this is the charge per unit volume. Now tell me, if I have now a solid object and it is charged, that means the whole of the object, inside and out. Now, what is the volume of a sphere? The volume of a sphere is 4/3 pi r cubed. Now, if this contains a total charge Q, then the volume charge density rho will be Q divided by the volume of the sphere, which is 4/3 pi r cubed. So, what is the unit for measuring rho, the volume charge density? It is coulombs per meter cube. If Q is the total charge on the object and V is its volume, then rho equal to Q over V. Most often used quantity is the surface charge density. But in our first example, we are going to use the linear charge density. Alright, let's talk about it. E, what does E stands for? The intensity of the electric field. Intensity of the electric field on the axis of a finite line charge. This is a finite line charge. You see, if I give some excess charge to this, how do I find the electric field produced by this, say, at a point on its axis, somewhere here? We cannot use the Coulomb's law equation that we used. We've got to modify that considerably. So, electric field on the axis of a finite charge. Now, here I have a line charge. Consider a long charged object of length L. This is the length L, and the linear charge density lambda. You understand what that is? With one end at the origin. So this end is at the origin. The length of the long charged object is L, and lambda is the surface, is the linear charge density. Tell me, if lambda is the linear charge density and L is the length, what is the total charge on this object? It will be L times lambda. Well, we need to find the electric field due to the charge on this at a point on the axis of this. We want to find the electric field at P here, a distance x0 from the origin. So the distance of point P from the origin is x0. Alright, so what does x0 stands for? The distance of the point P where we want to find the electric field. In order to do that, we are going to use the method of calculus, because this is an extended charged object. What we will do is we will take a small section of length dx. That will then act as a point charge, and then we can use the equation we derived already. So we take a small segment of length dx. This is the small segment of length dx at a distance x from the origin. So that is the distance x. Now, so that for all practical purposes it can be considered to be a point charge, and we can now use the point charge equation. We can now find the electric field at P due to this point charge. What is the equation for electric field at a point due to a point charge? It is kq over r squared. Well, tell me, what is the charge on this small segment? The linear charge density is lambda. In other words, charge per unit length. Therefore, what is the charge carried by a length dx? It will be L dx. The charge carried by this will be L dx. And what is the distance of this from P? The distance is x0 minus x. Is that right? Let's write that down. The charge on the small segment of length dx is lambda times dx. You see, lambda is charge per unit length. Multiply that by the length of the segment, you get lambda dx is the amount of charge on that segment. Alright. The field dE at P due to the charge on dx will be k q divided by r squared, where q equal to lambda dx and the distance r is what? The distance of this from P will be this x0 minus x. So we have dE equal to kq over r squared. That will be k lambda dx. That is the charge on this. And the distance is x0 minus x, and so you square it. This is the electric field at P due to this small segment of length dx. Alright? And this is dE, which will be directed away. The field at E, the total field E at P can now be obtained due to the entire object can be obtained by integrating this dE. You see, this whole object can be divided into many such small segments. The total field at E is the sum of the fields due to all such segments. Isn't that we call in calculus integration? So, in order to obtain the field E at P due to the entire extended object, what all we need to do is integrate this dE from x equal to 0. Look at this. The position of this element can change from this end, x equal to 0, to x equal to L. This segment can be anywhere from x equal to 0 to x equal to L. So E equal to integral 0 to L k lambda dx all over x0